Yes, sir.
Okay. Please let me know if there is any problem comes. Sometimes what happens in network and all issue comes. So please let me know, okay, whenever it comes. So good morning to all. Welcome to the session of modeling of DC-DC converters. We'll learn today a different approach named as bond graph approach. So how many of you have heard of this bond graph? Please note that this will be interactive session. I hope that it should not be a one way. So whenever I ask some query or ask some doubt or questions, please respond. Okay, so that it will be kind of, I also feel like interactive session. Yeah, how many of you have heard of this name, bond graph? Okay, fine. So now I hope that nobody has heard. Okay. Or they may not have idea what is bond graph. So what I will do, I have divided this lecture in two parts. First is to introduce what is bond graph, and then its application to modeling of DC to DC converters. Okay, so why we are applying bond graph approach to DC converters or in general power electronic systems. So this is a general block diagram of any power electronic system where you have a power input. V in can be AC, DC, anything. Then this is power output. V naught can be DC, AC, anything. In this, there is a power converter which processes the electrical power. Then there is a controller which process the control the power output or regulates the voltage. All these functions is done by this controller. The controller sends the signals, multiple signals, sometimes from output, sometimes from input, and with respect to reference is gives the control signals to the power converter to control the required variable. Okay. So that is the general power electronic system. So generally power converter consists of four types of power converters, generally AC to DC, DC to DC, DC to AC, and AC to AC. And this is a general block diagram of any power converter. There will be switch, there will be two storage elements, L and C, and there will be transformer. As per the applications, these elements will be changed. The only invariable element will be which one? All in this configuration, which will be the component which will be there by default in any power converter? Which will be that?
Passive elements?
Huh?
Passive elements will be always be there.
Quasi resonance?
Inductor.
No. I am asking, out of these four components, switch, L, C, and transformer, which will be the component which will be by default will be there in the power converter? Other components may be there, may not be there.
Switch.
Switch. No, switch, exactly. So switch is the power electronics heart of the power electronics switching. Okay, so switch, and then rest of the components will be as per applications. If you need filtering or if you need power, means sometimes power transfer processing or energy storage or the isolation, then all these transformer comes into picture and other components comes into picture. But switch will be by default there in any power converter. So as we can see, a power electronic system is a multi-domain system, multi-energy domain system. Okay, I have used this word specifically, multi-energy domain. So what is power electronic system? Is a consists of electric, magnetic, thermal, mechanical, hydraulic. Hydraulic, why it's coming? Sometimes a dry application. let's say it's a hydraulic drive or hydraulic system or pumping system, mechanical system, anyway, drive system. Thermal is by default there, magnetic and electric will be there in the power electronic system. So energy domains present in the power electronic system are, these are the general energy domains. Some other domain also may be there as per the application. So number of domains changes with the application. That is takeaway from this slide. But what is another takeaway is the power electronic system is a multi-domain system. So when we talk about modeling, that is we call as mathematical modeling. So generally we use I have shown these two models here, graphical models and mathematical models. But the approach of graphical models also to get the mathematical model. So mathematical model by default consists of ordinary differential and difference equation and state space equation. Graphical method consists of block diagram, you might be knowing signal flow graph, and third is bond graph. So these are the methods which are being used to model power electronic system. There are some papers which are also you might be aware of switching flow graphs. You can refer switching flow graphs. So these power electronic systems are also modeled by signal flow graphs. They have modified it as a switching flow graph to include the switching effect. Then ordinary differential equation and state space, these are usual methods to model power electronic system. You must have learned in the DC-DC converter modeling the state space approach, right? DC-DC converter modeling, you must have learned the state space approach and ordinary differential equation, first order equations. So now what we are going to see is a bond graph method. So why bond graph method? So, that has to do something with the multi-domain property of the power electronic system. So foundation of bond graph is the energy behavior in the physical system is domain independent. Okay, so domain independent in the sense, if you see from the energy point of view, it is not to do anything with the domain, that is electrical domain or magnetic domain or mechanical domain or rotational domain or hydraulic domain, nothing to do with it. Okay. And therefore, what is the idea is, if we use the same set of elements to model this domain independent with the energy behavior, you can use the same set of elements for multi-domain system. Are you getting my point? Are you getting my point here? You can use same set of physical system, same set of elements for multi-domain physical. This is very crucial point here. And further, like circuits, you have inductor, so you have inductor symbol. You have capacitor, you have capacitor symbol. You have switch, you have switch symbol. So therefore, in bond graph provides you one-to-one correspondence. So bond graph also has a similar elements, but they are modeled with the energy behavior. Similarly, causality feature, there is a causality feature. We will discuss all these points. And these causality features are useful for writing the equations, and which can be from which the state equations can be obtained. So these are the advantages of bond graph method. So as I said, energy flow. So there is an energy source and there is a destination load. So what are the phenomena which happens when energy got transferred from source to load? What happens? What happens? Yes, anybody's. When energy gets transferred from source to load, what happens? something happens in between, and then the rest of the energy transfers.
Yes, some energy is lost in the.
There will be loss.
Sir,
Exactly.
energy store,
There will be a
energy store
Lost energy.
in
yes.
partial
There
element.
will be a loss. There will be energy store. One is potential energy, and there will be energy store, which is kinetic energy, right? From energy point of view. So there is a energy loss, which is, and then there is a energy storage, potential energy storage, and there is a kinetic energy storage. So these are the storages which we have while energy transferring load source to load energy. So this is in you will agree with me that this phenomena is independent of physical domain. Means in the sense it occurs in every physical domain, right? It is an electrical domain or mechanical domain. This occurs in every domain. So therefore, what happens? Like we say that compare the inductor with the mass. So you must be aware of this this analogy. When you learn about modeling in control systems, you compare inertia with inductor. So mass is storage of what?
Inertia.
Inertia or kinetic energy, right?
Yes.
Mass stores kinetic energy. Similarly, inductor also stores kinetic energy. That is, we can say that continuity of current is a kind of a kinetic energy storage property. Or we can say that the current cannot change instantaneously in the inductor, whereas velocity cannot change instantaneously in the mass, right? That is the kinetic energy storage. Similarly, capacitor and spring, they are analogous. That is, capacitor stores charge, that is static, and the spring stores displacement, right? Kind of displacement. So it stores displacement. So that's why these are analogous. Similarly, damper in mechanical domain and resistor in electrical domain. So resistor is a representation of loss, and the damper is also a representation of loss. So these are the friction or loss. In general, it is energy loss. So we can say that the mechanical component behavior is same from the energy point of view. Okay, from energy point of view. So therefore, what we have to do is the bond graph philosophy has come from this property only. So it uses a basic physical mechanisms through energy point of view to form a set of elements. Okay, and it provides a facility to model multi-domain physical system using identical set of bond graph elements. So that's the advantage here, that even if you model mechanical system, even if you model physical electrical system, even if you model magnetic system, you use same set of elements to model this element, to the model in this energy domains. So now to further proceed, we have to understand some concepts. Now it is clear to you up to this point? Okay. So, okay. Now these are the some concepts which we have to understand while using bond graph method. Before using it, we have to understand what is the port and what is the bond. Okay. Because we say bond graph, so that is graph of bonds. So system, generally we divide in multiple subsystems, and the places at which the subsystem exchanges power with the rest of the system is called as port. Okay. For example, take a resistor, power through terminals of resistor or voltage source. Okay, so this is the power, this is the voltage at the terminal and current going in the resistor. So, and single set of voltage and current is associated with resistor or voltage source. Okay, so you can see that with this one port element, there is a single set available, that is V and I, right? This is two terminal elements. So there are two sets of voltage and current. One is V1 I1, another is V2 I2, right? So now if you interconnect all this system together, that is after connecting voltage source to primary, power flow through source and primary winding is same. Assuming that everything is lossless inside, so we can say that the power through voltage source and primary winding is same. Similarly, if you connect resistor at the secondary, you can say that power through the secondary winding and resistor is same. So therefore, there is an exchange of power, that is between voltage and primary, and there is exchange of power between voltage and the resistor and secondary, right? So that's the idea here, that the terminals, we can say that these are three subsystems: voltage source, transformer and resistor. The places at which the subsystems are connected and through which the power exchange between these takes place is called as port. Clear?
Yes.
Okay. Now, so if you want to represent this in the different manner, so we say voltage source, transformer and resistor. Then there is a, you can say one line is there with a one half arrow. Similarly, after transformer there is a line and with half arrow, with first arrow has V1 and I1 variable associated, second arrow has V2 and I2 variable associated. So we can say that line which connects subsystem indicates power flow between them and is called as power bond or bond. Okay, so generally inside implicitly it is a power bond, but to just reduce the number of words, we simply say it as a bond. And half arrow, just to differentiate, if you put full arrow, generally we use it for signals. Okay, so that's why to differentiate between power and signal exchange, so that's why this represented as half arrow. So half arrow shows energy or power direction. Okay, the direction of power flow. So now there are two subsystems A and B. Okay, and the power and energy flow between them is called as power bond or bond. So there are two subsystems A and B, and there are two variables associated with each bond, that is one effort and one flow. Now we have generalized voltage and current, effort and flow, because we have to make it as a domain independent. So now this bond, we can represent it as the power is expressed as a product of two variables which can be easily measured and gives physical interpretations. Okay. So these are called effort and flow variables, where power is multiplication of effort multiplied by flow. And this bond is represented like this, which has two variables associated with it, effort and flow. Is it clear?
Yes.
Yes, sir. Yes, sir.
Okay. But now effort and flow variables, we have to choose in such a way that they should be easily measured and gives physical interpretations. Okay. That's the main concern we have to have. So generally, now this is the general representation of bond, is labeled and directed graphical representation of physical system. Okay, so it's a labeled like effort and flow, and there is a directed, that is the power flow is direction is shown.
Sir,
The symbol I line with a
Excuse me,
half arrow. Yes,
sir, it is unidirectional or bidirectional? I don't.
it's a unidirectional.
So, sir,
No, in the
this
sense,
advantage,
see, no. It is for, I'll come to it. Okay.
Oh.
Whether it's a, you assign some direction,
hmm. Sir,
right?
this effort and flow are basically look like force and time, like power equal to force into time. That way.
Power is equal to force into velocity.
Uh, that way only.
Yeah. Okay. But
Okay.
you assign some direction.
Hmm.
If it is opposite direction, it will come something like negative. It is to generally this arrow is useful in writing equations,
Hmm.
to obtain equations. Okay. Finally, we have to, what is the use of modeling? We need to have some simulation or some simulation for which we need mathematical equation. So final goal is to obtain mathematical equation, right? So if you assign some direction, let's say, and your calculation come opposite to it, then you can infer from it that the power flow is actually opposite direction. Are you getting my point?
Yes, sir. Yes, sir.
Oh, okay. So there are two variables with each bond, effort and flow, the product of which is power. So I am again and again repeating this, that this bond is represented like this with a half arrow to differentiate between signal and power flow. Okay, and there are two variables associated with each bond, effort and flow. That's the main idea. So we can have multiple domains like this, where effort is force in mechanical, velocity, or in mechanical rotational, torque and angular velocity. In electrical, it is voltage and current. In hydraulic, it is pressure and volume rate. In thermal, it is temperature and entropy change rate. In chemical, potential, mole flow rate, enthalpy, mass flow rate. Of course, I don't know, these are measurable. Okay, but must be measurable, mass flow rate and all. And in the magnetic domain, it is MMF and rate of change of flux. So these are the variable in the different domains which are generally measurable. So now based on port, there are into three categories. Bond graph elements can be divided into three categories. One is one port elements, another is two port elements, and third is multi-port elements. So which are the one ports? One ports are effort source, flow source, resistor, inductor, and capacitor. See, we are from electrical domain, so that's why we have used this terminology. But these are nothing to do with the electrical. Are you only with electrical? Are you getting my point? This describes the effect actually. If I say inductor in bond graph, what does it mean?
Energy storage.
Kinetic energy storage.
Sorry, not energy storage.
Okay. And capacitor means potential energy storage. Resistor is a representation of loss. Okay. Effort source, flow source. Effort source means, let's say, force. Force is a effort, or MMF is a effort. Okay. Flow means current is a source, or velocity is a source. So that is a flow source. So see, this is a mathematical modeling method. You observe the phenomena in the given system, and you try to put it on pen and paper. Using pen and paper, try to model that system. As if you observe some loss, you will model it as a resistor. If you observe that there is a kinetic energy storage, you will model it as inductor. If you observe that there is a potential energy, then you can model it as capacitor. So this is one port. Two ports, so transformer and gyrator. I'll come to it what is gyrator, but you must have heard this term gyrator. Have you heard of it?
No, sir.
Gyrator. I'll come to it what is gyrator. So transformer and gyrator. Note again, this is nothing to do with electrical. transformer means it's a two port element. That's way, in that way you have to take. And multi ports, one junction and zero junction. One junction means from electrical point of view, we can say that it is loop, and zero junction we can say from electrical point of view kind of a node. Okay, that we will also understand what is it. So we'll start with a one port. Now one ports are effort source and flow source. Now in effort source, you can see E and F. So what will be fixed here? Or what will be clearly defined here in effort source?
E will be effort.
Effort is clearly defined. Right?
Hmm.
Flow will be depend on external system. Similarly, in flow source, flow is clearly defined, and effort will be decided by external system. Okay, I'll come back to it again. We have to come back to it with some different context. Similarly, there are modulated sources, right? For example, sinusoidal, effort, or flow source. So there is a you can say it's the same as effort source and flow source. Only thing is modulated, or PWM inverter, right? So there's a modulated source. Similarly, resistance. So there are two governing equations. Now one may ask, how will you decide this governing equation? We'll come back to it subsequently. So effort, you can see now there is a bond and half arrow. So this resistance is defined like this, right? So governing equations are either E is equal to FR or F is equal to E by R. Provided, what is the basic condition to follow this equation?
That R should not be equal to 0. In that case, F will be infinite.
Yeah, R is equal to 0 is a special case. R should be linear.
R should be linear.
Yeah, then only this equation will be followed. Or in general, what will be the equations? E is equal to some function of F, right? Or F is equal to some function of
E.
So these are the general equations. Okay, but this will represent the loss. Are you getting my point?
Yes, sir.
Okay. So this R we are taken as linear equation, or R has a property like on effort and flow domain. If I take a effort and flow, it is having a linear property. Okay, that's the idea. Now, next is inductor or inductance. So the governing equation are either L is equal to df by dt or F is 1 by L integral of E dt. Again here, what is the assumption?
L should be linear.
L should be linear. On which plane?
Means, sir?
Plane. What will be the plane where L should be linear for say electrical domain? Say in electrical domain.
Not able to.
V and I.
Huh?
V and I.
Voltage and
E and
current.
I.
Yeah.
No.
F and D.
Flux, current,
Flux current.
right?
Yes.
In electrical domain, specifically. Electrical domain, you have flux and current. If it is linear relations, that is L. Yes or no? Because relation you must be knowing, right? Phi is equal to, correct?
I equal to d phi by dt.
No, phi is equal to
E
Li.
equal to phi equal to
Phi is
Li.
equal to Li.
I equal to phi by L.
So phi by I is L. So that's the idea. So assuming that this inductance or this is a linear, and is it in any domain it is linear only. So these equations are valid. Okay, that is E is equal to L df by dt, and F is equal to 1 by L integral of E dt. Okay, that's the idea. Similarly, for capacitor in electrical domain, what should be the linear capacitor? Which plane?
Q and V.
Q and V. Good,
Q equal to CV. From that we can.
right? And the slope is C, right? So Q is equal to CV. Assuming that in any domain this potential energy storage, this property is linear, then these equations are valid. Okay, that's the idea. Otherwise, there will be a non-linear equations, but still it will model still energy storage only, right? But for example, if say E is equal to in electrical domain, that is most comfortable domain right now for us, electrical domain, either F is a function, E is a function of Q, or Q is a function of E, right? Where F is a nothing but dq by dt. Are you getting my point?
Yes, sir.
Yes, sir.
So or this is for non-linear. So this flow and will be related, E and F will be related by then a non-linear capacitor equation. But then these equations won't be valid. The governing equations here which I have shown, they won't be valid. They will be valid only for linear elements. Now transformer. So now transformer has two properties, either. So E1 and F1, E2 and F2 will be two, there are two bonds associated with transformer, and there is a modulation M. So E1 is equal to M E2 and F2 is equal to M F1, right? So that depends on that, depends on what you take M, right? For example, this M must be in electrical domain. Let's say this transformer is there in the electrical domain, which we are representing as a bond graph like this, which is shown here. So if it is M is to 1 and E1 E2, then you can say that E1 is nothing but M E2, right? Yes or no? And then F2 is nothing but MF1. Correct? Yes? Okay. Now if it is 1 is to M, then E2 is nothing but ME1, F1 is nothing but MF. It depends on that. So these equations are independent of, these equations are depend on how you take M. Okay, the message here is now that effort is corresponds to effort here and flow is correspond to flow here, right? Now if one effort is, for example, if E1 is defined, E2 will be automatically defined, and if F2 is defined, F1 will be automatically defined. So here either one of them defined on the left side and on the right side, the rest will be automatically defined. Are you getting my point?
Excuse me, sir.
Yes.
Sir, in the second case where you have mentioned 1:m, the direction will remain same or it will also get changed?
Where?
So in the
So
second
direction
case,
is
as you
I am keeping as independent. I have shown direction,
Okay.
but it is keeping as independent.
okay, fine, sir. Thank you.
That's why I removed that direction. Direction is not matter for us. It may then the sign change and all may be there, but my message is what I want to give here is they are related like that. Okay. Now comes to the gyrator. This is interesting. Now you can see it from the equation. E2 is related to flow of bond 1 and E1 is related to flow of bond 2. Interesting, right? E2 is directly related to flow of bond 2 and E2 is directly related to flow of bond 1 and F2 is directly related to effort of bond 1. So you can see that E2 is nothing but MF1 and E1 is nothing but MF2. Correct? So that is the gyrator equation, right? In gyrator, there is a cross linking. That is, effort on one side and flow on other side are linked directly. And in transformer, effort is directly linked to effort, flow is directly linked to flow. Is it clear the differentiation?
Can
Yes,
you
sir.
please?
Okay. And then there can be a modulation. Okay. There can be a modulated element. So now multipole, one junction, right? These are very important. Okay, this multipole junction to overall generalized modeling of the system. You can see that there are 3 bonds associated with one junction. So you can see that E1 plus E2 plus E3 is equal to 0, while F1 is equal to F2 is equal to F3. What is it analogous to?
KVL and KCL. Like, hello?
I will not say KVL. KVL, there can be difference. I will say series connection. Correct?
Yes, sir.
Series connection, flow or current is same and total voltage is summation of 3 voltages if there are 3 elements connected. So E1 plus E2 plus E3 is 0 and if they are connected in loop, say electrical domain, this kind of, we can say that the flow is same E1, E2, E3. So plus minus plus minus plus minus. So E1 plus E2 plus E3 is 0, but however F1 is equal to F2 is equal to F3. So this can be represented as this, we can say that R1, R2, R3. Are you getting my point?
Yes, sir.
Like this you can model. There are 3 elements connected in series, so one junction. Okay. And there are Obviously node. So there are, from electrical point of view, F1, F2, F3, E1, E2, E3. So obviously E1 is equal to E2 is equal to E3, F1 plus F2 plus F3 is 0. Correct. So this is nothing but model as zero junction. So how will you model? 1, 2, 3, that is R1, R2 and R3. Clear?
Yes, sir.
Okay. So like this you can model this. For example, now this has shown only 3 bonds, but this can be generalized to
Four
multiple.
bonds.
E1 plus E2 plus E3 plus En 0. Similarly, F1 is equal to F2 is equal to F3 is equal to Fn. So there can be n number of bonds, depends on the what model we are and how is the energy flow. Now you can see that the flow is same in this connection and effort is same in this connection. So depends on how you model this, depends on how you model the system and what are the effects you observe. So these are the 9 elements, basic elements, which we can model multi-domain system. Now seamless representation, right? Seamless, and you understand the word seamless. That is mechanical, electrical with the same elements. So you don't need to transfer. And this is due to the fact energy behavior in the physical domain is domain independent. So that is the idea. Now very important concept we have to see. We have now here previously, how will you write equation? So this is how you write equation. But now when you write equation, something has to be on left side and something has to be on right side. Agree?
Yes, sir.
Right. This is all on the what you call left hand side only. What should be on the right side and what should be on the left side? Then only we can solve the equations, right? So that is the important concept called causality. Okay, causality. So causality, for example, here I have applied voltage source across the resistor. So what is causes current? What is voltage is causing current, right? So cause is voltage, effect is current. Similarly, if I am applying a current source, cause is current, effect is voltage. That is equation. If it is a linear resistor, equation simply is I is equal to V by R when voltage source is applied, and V is equal to IR when current source is applied. Correct. So now therefore we have to see which is cause and which is effect. Correct. So now here causality represents cause and effect relationship between effort and flow variables of the bond. And when you want to once you form the bond graph, you need to obtain equation. So you need to have cause and effect variables. You need to decide cause and effect relationship between effort and flow. So that's why you give a causal stroke to decide which is cause and which is effect. So that's why we call it as causality. So causality is represented as perpendicular line at the one end of the bond, and this line is called as causal stroke. For example, if I apply, there are two subsystems connected, and if I give a causal stroke at this point, you must be able to see arrow.
Yes, sir.
So this is a causal stroke. So what does it mean? A is applying effort on B, in turn B is applying flow on A. Or A is applying effort on B and flow is the effect of that.
Sir,
So effort is cause, flow is effect.
hello.
Yes.
So in second or third slide, you have shown one table in which for electrical system the effort is voltage and the flow is current. So now here cause and effect are getting changed. Like voltage also becomes cause. If you
Here.
yeah.
No. I am more focusing here how to obtain equations here. So if voltage is cause here, right? How current will vary? Current is a function of voltage if resistor is constant.
Yes, sir.
Are you getting my point? So what is cause here?
I'm actually I'm just actually confused in between. What I gain was the effect in electrical system is voltage and the cause is the current. Now here in causality, the there's an interchange also. Like cause is current also, cause is voltage also, effect is voltage also, effect is current also. So it is we don't have to map it with the effect and flow. It's different thing. It is like that, sir.
Miss, can you repeat again? I am not able to hear it properly.
Like in electrical system, the effect is voltage. The flow is current. This is what we have shown in the table on third and fourth slide.
Yes.
Now in causality, see the effect is voltage, cause is current, and effect can be current and cause can be voltage. So I'm just mapping it with the causality. The first, the table which is on the second or third slide. I'm just mapping it with the causality. So I'm getting confused. So you're getting me what I want to say.
No. See, in any bond, right? What is the effort and flow? Power of it should be, the product of should be power, correct? While causality has to nothing to has to decide which is cause and what is effect. Causality has some different purpose here. Purpose of causality is to obtain proper equations, right? If you remember when you solve circuit, right? Sometimes you take voltage, sometimes you take current on the left hand side, right hand side.
Yes, sir.
Right. So here you can see that's what I want to stress here. Emphasize that if I know what is cause here, the equation is on the left hand side there is a current and on the right hand side the variable is voltage. In general, on left hand side there is a flow and right hand side there is a effort. But whole purpose is to obtain equation. But however, we can see that the cause and effect, the flow and effort variables are same in electrical domain. I hope I answered your question.
Sir, this we can remember like this, that if that the what is the that means the output will be the effect. Suppose if in this slide only, if we want to get current, so that will be output. So that will be effect.
No, I will not say it's output. Again. It is not output. It's a effect and B is a cause.
Okay, sir.
Okay. I need to obtain some equations, right?
Sir, I need to know that what is the difference between, if there is a difference, between cause and flow.
No. Cause and flow, no. Cause and effect. Cause and effect. If cause is flow, next slide, that is cause is electrical domain I have taken because it's most comfortable to all of us. So if cause is current, what is the effect of it? If I applied across linear resistor, voltage across resistor. So
Yes,
all
sir.
this flow here, and effect is effort. Cause is flow here, effect is effort. So what is the equation I have obtained? V is equal to IR. Because if I is, yeah, cause can be either flow or effort. That's the idea. But that you have to decide. I
Oh,
hope
Yes,
you
sir,
are
clear.
getting.
Yes, sir, clear.
what I get is the current can be effort, the voltage can be effort, and the voltage can be flow, the current can be flow. It's like that, sir.
Yes. Yes. Voltage
Ah,
can be
yes.
no. Voltage will be effort only, always.
Always it will be effort, sir.
Yes, yes.
Ah,
I'll come to it. Now I'll come to it. Now this is the concept. Okay. Now V is equal to IR. Now I want to emphasize here. If I am applying I across R, I through R, what is the voltage across R? V into IR. V is equal to IR. What is on left hand side and what is on right hand side? Main emphasis is obtain equation. Correct? Now how will you translate into bond?
Sir,
Yes.
so can we define causality in terms of resistance as Ohm's law?
Causality in terms of?
Resistance as Ohm's law?
See, I have taken this example as a Ohm's law because we are most comfortable in electrical domain. All of you will agree.
Yeah, yes, sir.
Yes, sir.
Yeah. So that's why I have taken this example.
Okay.
Okay. So nothing to do with Ohm's law. I am always emphasizing here. This is a general example. If R is linear, obviously Ohm's law will be followed. So V is equal to IR. Main emphasis is not that. Main emphasis is what is on left hand side, what is on right hand. Right?
the effect will always be on left hand side.
Effect will be on the left hand side, and cause will be on the always on the right hand side. So cause can be either effort or flow. Effect also can be effort or flow. If flow is on the left hand side, effort will be on the right hand side. If effort is on the left hand side, then obviously flow will be on the right hand side. In general, what is the equation? E is equal to FR for this. So what is cause here and what is effect? Flow is the cause, effort is effect. Right?
Yes, sir.
I think I'll take next example so it will be clear to you. This you understanding here? I am applying effort, that is, let's say this is voltage, this is resistor. So what is I am applying? Effort here,
Voltage.
voltage. What is coming out?
Current.
Current. Right? So there are two variables associated. Now I am applying voltage here on the B, current is coming out. Similarly, if I am applying now current, this is current source and they say this is resistor. If I am applying current here, what is coming out? Voltage. Right? So now this is B is applying effort on B. If you see from B side, what is happening? B is applying effort on B. B is applying effort on A. In turn, A is applying flow on B. Okay. Okay. Now don't will not get stuck here. If I go further, then it will be more clear to you what I am going to say. Now, with this, we have to apply some causality rules. Now, if I have a voltage source or in general effort source, what should be the causality? which is I am showing here. So in
If
flow,
effort
this is
source,
what is
then current means flow.
effort is fixed here, right?
Uh,
Flow is effect,
yes, sir.
right? Similarly in flow, if you then you have to give this causal stroke in effort source like this here. Okay, because you are applying effort on something. Similarly in flow, if you have a flow source, flow is fixed, while effort will be the effect. Flow is cause, effort is effect.
Yes, sir.
Yes or no?
Yes, sir. Yes.
Yeah. So that's how you have to give causality like this. Okay. And this, see, this arrow, it decide, see, arrow is for your equation orientation, right? So this will give you me left, this causal stroke will give me left hand side and right hand side, and this arrow will give me a sign, plus or minus. Are you getting my point?
Yes, sir.
Okay. I'll take one example later so that it will be clear to you. So for elements other than sources, if the effort is a cause, then causal bar is at the arrow end of the bond. This is for our comfortable, nothing to do with arrow. And flow is the cause and causal bar is the non-arrow end. Nothing to do with arrow, but still for our comfort only. What does it mean is, if effort is cause, stream A and B, right? Then on this arrow end, and if flow is cause, so nothing to do with the arrow. Arrow is for generally a sign in the equation. Now causality rule 3. So only one causal bar at the junction or zero junction. Now if I give one analogy, it will be very clear to you why and what does it mean. So at the zero junction is equivalent to what?
T junction. Node.
Parallel connection. Actually, no, not node also, parallel connection. Right? Parallel connection. So if I say that there is a bar at zero junction at one side, exactly at zero junction, what does it mean? Something is applied effort here. For example, if voltage, it's a voltage source. Correct? So if it is a voltage source, by effort and flow, we have decided voltage is what? Effort source. Yes or no?
Yes, sir.
Voltage is effort source. So that's why we have put this causal bar at the zero junction. Now once it is fixed, can we put another causal bar here? No. Why?
Because effort source is because
Because
source
it will
is
be
flow.
like, it will be like
Flow source.
Is it possible if they are not equal? No. So same thing is happening. You can use this analogy to understand. Okay, so that's why you have only one effort, only one causal bar at the zero junction. Now you can see the governing equations here. What is deciding the effort at zero junction? Bond 1, correct? Bond 1 is deciding effort. So therefore E2 is equal to E1, E3 is equal to E1. Other bonds automatically the effort is decided, that is E1. Similarly, F1 is decided by summation of F2 plus F3. It is like this. Now, if I apply voltage here, what is the voltage here? V. But what is the current here? In the effort, I1 plus I2 plus I3.
I3 equal to 0.
No. I1 plus I2 is equal to I3 if whatever is the source. What is I? If this is I1, I2 and I3, what is I? I1 plus I2 plus I3.
Yes.
Same thing here. Same analogy. Okay. So this is rule for, so only one causal bar at the junction and all others are away from the junction. So this is one important rule. Otherwise it will be violative. Similarly, one junction, only one causal bar away from the junction and all other towards the junction. Now here the governing equation is E1 is equal to E2 plus E3 and F2 is equal to F1, F3 is equal to F1. Okay. So what does it mean? For example, simple example, let's say there is a current source with two resistors in series, and this is say F1. I'll take the same thing, right? The effort across this is E1. Here effort across this is E2. Flow across this is F2, this element, and flow across this is F3, and effort across this is E3. I hope now it is clear to you what is this equation is. So what is F1? What is E1 then? E2 plus E3? Yes or no? And what is F1? Is equal to F2 is equal to F3. Correct? Same thing. Series connection. Now, one junction, only one causal bar away from the junction, all other towards the junction. Okay, so that's the idea here, that in series connection only one flow will be there, right? So obviously only one flow and all other flows are same as this F1. So F2 is equal to F1, F3 is equal to F1. I think we'll move slightly faster, but I hope these are the main rules which are, I hope it is clear to you.
Yes, sir.
Okay. Now similarly resistor. I hope it is clear to you now. What we have discussed the earlier example. If flow is the source or the causal bar is at the left hand side is equal to Fr. And now governing, if causal bar is on the right hand side is equal to F is equal to E by R. What is cause here in the second? Effort.
Effort.
Effort is the cause, flow is the effect. In first equation, flow is the cause,
Effort is the
effect.
effect.
Okay, so that's the idea. Similarly, for governing equation for inductor, linear inductor, we can say, or in where this property is linear. Then it is a derivative causal, that is equal to L di by dt or L df by dt. The governing equation when flow is a cause and effort is effect, and when effort is cause, flow is effect, then is the integral equation. That is F is equal to 1 by L integral E dt. That is when we write like this, F is nothing but 1 by L 0 to T E dt. Correct? So this will be the equation. So generally integral causality is a preferred causality. Why? We'll see that. Okay. Integral in general also we generally prefer integral. Right? When we write state equations, we generally prefer f is equal to 1 by L dy by integral dt, or I is equal to 1 by L v dt integral. Similarly for capacitor, the governing equation is E is equal to 1 by C integral f dt, that is V is equal to, for example, in electrical domain 1 by C 0 to T
IDT.
dt, right? And in electrical domain I is equal to
C dVc by dt.
T dV by dt, correct? So that's the idea. So this is derivative causality. When we say that effort we are applying on the across the capacitor, it is a derivative causal, because there is a derivative equation, derivative there, and here is an integral, so it's called as integral causal. So integral causality is a preferred causality because it is easier to obtain equations. Similarly, when you apply, for example, M, there is if you are applying effort at the transformer, then E2 is equal to ME1 and F1 is equal to MF2. That is E2 is equal to ME1, that is we are applying effort at the transformer, so E2 is a function of E1. Similarly, we are applying F2 at the transformer, so therefore effect is F1. Are you getting?
Yes, sir.
First you see from here for effect point of view, from effort point of view, then you see from here from flow point of view. So when you see from this side, how it will look like? Flow source, correct? So effect is what? F1 is equal to MF2, and from if you see from this side, which I am showing arrow, it's a effort source, and it so effect is also effort, and same thing is here. Now here I am applying a flow, so the on the F2 is a function of F1 and E1 is a function of E2, because E2 is actually indirectly applying effort on the this terminal. So like this you should be able to see. Gyrate is more interesting, gyrator. Now you see the causality here. If I apply a flow causality at the left hand side bond, then right hand side bond will be automatically, causality effect will be on this side. The causal bar will be on the other end. While in transformer, what is there? If transformer I am applying bond here, the causal bar here, so it has to be on the other end only. But in gyrator, if I am applying a causal bar on the left hand side, then the causal bar on the second bond will be on the right hand side, because you can see the governing equations. Are you getting my point?
Yes, sir.
Okay. Similarly, if I apply effort at the gyrator, the cause will be on the other bond there will be flow, means they are on the same side. So that's the idea. Now the most important advantage of bond graph is, once you form a model, you can obtain easily a state equation. Okay, so that's why you can easily obtain the state equation. So this also we generally use when you must have done this exercise in control. When you obtain the equation of RLC circuit in a state form, you generally consider two energy storage, right? So energy storage
Yes, sir.
elements in bond graph, similarly the similar effect having, that is inductor and capacitor, right? Two energy storage elements. So here also there are two energy storage element, that is inductor and capacitor in general form. in the sense not only limited to electrical domain. It is also it's a energy effect, and causality should be integral causality. I hope you will be able to correlate with the state equations. Are you?
Yes, sir. Yes, sir.
Yeah. So there also use integral causal. So the bond graph, the number of state variables is number of integral causal elements. Okay. Or in state equation, number of state variables are
Number of energy storage elements.
how they are connected. That also affects, right?
Yes, sir.
If let's say there are 3 inductors connected in star, how many state variables will be there? If there are 3 inductors connected in star connection,
State variable only one will be there
there will be
inductor
2
only.
state variables.
Two.
Because by KCL, third inductor current will be summation of 2 other inductor
Right.
currents.
2 other inductors.
While you can obtain the state equations for only 2 inductors. So that's why you can. So bond graph gives you the facility. So when you have such connections, okay, then number of integral causal elements, whichever are number of integral causal elements, number will be state variables. That's a straightforward. Here you have to write equations and then obtain. Okay, if I write like these equations, then only. But in bond graph, after seeing, after writing a graph, after assigning causality, you can immediately get how many state variables are there. Okay, so that's the idea. So this we have already discussed, right? So in integral causal inductor, governing equation is flow is 1 by L effort dt, and integral causal capacitor, governing equation is effort is 1 by C flow dt. So state variable is effort in integral causal capacitor, and state variable is flow in integral causal inductor. So inductor and capacitor with derivative causality indicates dependent energy storage elements. Okay. And energy variables of dependent energy storage not algebraically independent of another energy variables and source constraint. So I'll take one example with this. Now take this circuit. Okay. Take this circuit. So now we need to obtain the bond graph for this circuit, and then final aim is to obtain equations which we can use for simulation. So we need to identify each the block components share the same flow. So how many block components share the same flow? I have already marked them. That is voltage, resistor, inductor, and capacitor and resistor in parallel. They share the same flow.
Yes, sir.
Similarly, the load resistance RL and C share the same
Why
effort.
you have taken
Huh?
why you have taken capacitance and resistance in the same block, sir?
Yes, I'm not getting your voice is slightly what?
Sir,
what
why you have taken capacitance and resistance in the same block?
Because they share the same flow. The overall block share the same flow. I'm not saying individual components share the same flow, but in combination of RL and C share the same flow or same current. Do you agree?
That is for ideal capacitor, no, sir? Isn't it?
No. See, if you go by KVL, right? Not KVL. Do you agree that current of Vs, Rs, and L is same?
Yeah, definitely, sir.
What about this?
The current will be different.
Current will be different individually. But what about the combination? Overall current is same.
Yeah. If we are taking a
So they share the same.
combinational,
If you combine it, say, let's say there are two resistors in parallel. If you write an equivalent resistor there, flow is same.
Yes, sir.
Right? So they share the same flow. So therefore there is a one junction. Because one junction elements share the same flow. Similarly, C and R share the same effort.
Yes, sir.
So there is a zero junction. Okay. So same flow, one junction, same flow, same effort, zero junction.
Okay, sir.
That's the idea. So therefore, what we'll do now, take this circuit. There is a Vs, that is voltage source. Then there is a Rs. Then there is a L. And then there is a zero junction. But mark here, there is a voltage and current, the flow is same here. While zero junction is RL and C, correct? Is it analogous to this? Is circuit visible here and this?
Yes, sir.
Correct. So if you are aware of this the method, you can immediately write equivalent electrical circuit as well. Okay. Now assign time to assign causality. So for voltage source, what is the causality? Effort source. Voltage is nothing but effort source. So I assigned here first sequence is source. Okay, so we have to assign the causality in sequence. First sequence is source. So that is fixed causality. Then what is another fixed causality? Integral elements. So we prefer generally integral causality. So you assign first that integral causality. Then junctions, and junction rule is what? At one junction, only one causal bar can be away. Yes or no?
Can you please repeat this, sir?
Okay. Source is fixed. That you understood?
Yes, sir.
Source causality. Okay. Source is applying. We are supplying the source at one junction. Now next is dynamic element. So in previous example, what is the preferred causality? Integral causality. Right? So what is integral causality here for L? Away
Yes,
is
sir.
effort you are applying. For similarly for capacitor, integral causality is this, the first example. So therefore, if you go like this, first is source, then dynamic element,
Okay.
that is integral causality we are assigned to this. Now what is the junction rule? You have to follow junction rule.
Okay, sir.
So at zero junction, how many effort source can be there? Or how many causal bars can be there at the zero junction? We have seen that rule, right?
Only one.
Only one. So obviously, where will be the other causal bars? Away,
Okay.
away from the zero junction.
Yes, sir.
And at one junction, only one causal bar can be away from the one junction. So other causal bars will be
Near to it. Okay.
near the one junction.
And
So therefore, We have assigned like this. So dissipative elements can be at last. Okay, dissipative elements can be as last. So because there are no fixed causality there, whichever you are comfortable, in that way, which other rules should get followed, then you can assign the causality to rest of the dissipative elements. The last option.
Yes. Thank
Now,
you.
which
sir.
are the state variables?
L, C,
IL,
and IL.
right? So IL is
IL.
what? At one junction, IL is fixed because that is the integral causal. So IL is a resultant. So what is IL is fixed. So what will be the flow at other junction, the other bonds in one
E.
junction? IL,
IL will be.
right?
Hmm.
Similarly, at zero junction,
VC,
if effort is fixed, so what will be the flow at other junction?
VC only.
VC, right? Fine. Now at each bond, what will be the effort of, sorry, what is LDIL by dt? Summation of effort of all other bonds. Yes or no?
Yes, sir.
Right? So summation of effort of all other bonds. So therefore, and at zero junction, summation of flow of all other bonds. Correct?
Yes, sir.
Now everything is obtained now. So LDIL by dt Vs minus IRS IL minus Vc, dduc by dt is IL minus Vc by RL. So therefore, we can easily obtain state equations.
Yes, sir.
Correct? Do you want one more example?
Yes, sir.
Okay. We are not able to go to power electronics, but let's see. I'll cover it lightly. Because till now, but how you find this technique?
It is a good technique to remember.
Yeah. So now let's say,
Sir, what is the difference? Like we are getting the same state matrix, same space representation. What we will be getting through state space representation.
yeah, state matrix.
What is the difference?
No. What is your question?
Like if I'm doing with that conventional method, if I'm doing with this bond graph method, what is the difference? Like we are getting the same results.
You are getting the same results, but your effort of modeling the system will be reduced here. There you have to write each equation. You are simply, what you can do, this you can computerize this method. In fact, there are softwares available. You simply connect the bond graph and get the equations. But also, if you, let's say, I'll take one example here.
Exactly.
It's the example which I was talking about. Let's say this is I1, I2, I3, R1, R2, V, S. Okay. So what is the bond graph here? These two are in parallel, right? So there is a one junction, PS, 1, there is R1, this is L1, there is L1 and then there is a zero junction. Correct? At zero junction, there is
L2
L3,
and R2.
then there is again one junction because L2 and R2 in series,
Hmm.
L2,
L2, R2.
R, right? So now assign causality. The R will be at last. Okay. R will be at last. First is effort, that is Vs, correct? Then let's say we assign all integral causal, that is L1, L2 and L3. Integral causal. So now we have to see which will be the rules of the by rule only one bond can be away, one causal bar can be away from the one junction,
Yes.
right? So with this rule there should be like this, and if it is here then there should be like this. What is the issue here?
In this, in the front of one junction, both sides bond facing to one junction only.
No, there is no issue at one junction, but there is a issue at zero junction.
All are away, sir.
Both are away.
There should be at least one causal bar at zero junction.
Yes,
Yes,
sir. And
sir.
here all are away from zero junction.
Huh?
All bonds are away from zero junction.
Yeah, all bonds are showing causal bars away, but there should be at least one causal bar at zero junction, right? That
Yes,
means
sir.
what? Some of the modeling issue is there. So if you put this, right, then it is satisfied.
Yes, sir. Yes, sir.
Now, with this, if I show you this bond graph directly, instead of showing this circuit, if I show you this bond graph directly, how many state variables are there?
IL2, IL3.
No. What is my statement earlier, which I have shown? State variables,
IL1 and IL3.
variables is equal to number of
Integral.
integral causal. Which are the integral causal here? IL1,
IL2.
L3.
IL,
I-
right?
Hmm.
So what is the flow here then? If it is one junction, IL1, IL2,
Hmm.
and if this is, let's say, IL3
Hmm.
and EL3.
Hmm.
So what is EL3 then?
EL3 will be
DIL3 by L3
DT.
into DIL3 by DT, right? What is IL3? IL1
IL3 1 by
minus
IL2.
IL2. So this is one algebraic equation,
Hmm.
and rest are, if you want to
Differential
write,
and integral equation.
rest are integral equations. So which are those integral equations then? L1,
IL1 equal to
no, IL1 DIL1 by DT is
DIL1
equal to Vs minus R1
into minus
IL1
R1.
from bond graph itself you can see and immediately write minus
Hmm.
EL3,
Huh.
because what are the effort at all other bonds? EL3. If it is fixed here, right? EL3, then EL3. Similarly, L2 DIL2 by DT is equal to EL3 minus, what is the effort here? IL2 R2.
Into R2.
That's it. Got it. These are two integral equation, and this is one algebraic equation. So by just looking at bond graph, you can write this. Are you getting the advantage of it?
Yes, sir.
Noticing the advantage is when we write circuit and when we write bond graph, immediately with causal bar, causal assignment, immediately you can get which are the state variables and which are the dependent variables. Yes.
Can you please, hello, sir, can you please just tell me that why you have chosen IL3 to be in the algebraic equation? It can be IL2 also.
Yeah, it can be anything.
IL2 also can be an algebraic equation. Then we'll get the integral causal in terms of IL3. It can
Yes,
be.
IL3.
It can be possible. Either way.
That is your choice. Yeah, anything. Even L1 can be also integral derivative causal.
Okay.
That
Excuse me,
depends on
sir.
how you assign causality. How you assign causality. Are you getting my point? But you can conclude here that there will be only two. This is only two order, second order system, right? Because there are only two state variables. Clear?
Excuse me, sir. Here you
Yes.
have
Causality we are defining as per junction. Hello.
Yes, junction rule has to be followed.
As per junction, we are defining the causality. So, does it play any role that for algebraic equation we have to select IL2, or for algebraic equation we have to select IL3?
Okay, we will see
You
one
have
more.
selected IL3.
Right? Yeah, I selected IL2. Let's say there is another possible causal configuration here. This is one. You see, important is we have to follow first effort rule and then junction rule. Correct? If you assign here, let's say, correct? And if you assign here, for example, let's say I have assigned causality like this.
It is T.
Correct? Then first we will assign integral causal to both. And then what about this then? It has to be like this. So where is the junction rule is violating? At zero junction as well as at one junction? One junction, at zero junction it is violating, obviously. So what we have to do is what we have to do? We have to change we can change the causality of R1. This assign this. Now it is followed. R1 is in our hand, or register causality. Again, now the dependent variable is L1. Okay. So that's right.
excuse me,
So
sir.
after
This was
seeing
my
the bond graph, you can immediately get which are the integral, how many state variables are there. You can immediately make out.
Sir, understood, sir. But for the dependent variable, how we will put that thing is in control, because we will not be getting the whatever you have to control, like IL1 and IL2 to the denominator is D. So we'll be getting IL1 by D or IL2 by D. We will not be getting IL3 by D. So how to control that? So you are getting me what I want to say.
No, we are not going to control anything. Here, how you assign your causality will decide what will be your dependent variable and what will be your independent variable. That is the emphasis I want to show here. That is the message here. How you assign causality by following junction rules has to be followed. They cannot be violated. And effort also. But all other can be.
So I got the point, sir. But that's a general thing that I'm asking. That's this is for after getting the equations, we'll be deriving transfer function like IL1 by D, something like that. By like let's say I'm taking the example of a converter. So IL1 by D and IL2 by D. This is how I'm defining the transfer function. This is how I am designing the controller as per the transfer function to get the required phase margin. And this is how I'm controlling my IL1 current and IL2 current. Like it is like that. So how to control IL3 current if it is an algebraic equation, sir? You
IL3 by controlling IL1 and IL2, because IL3 is nothing but IL2, IL1 minus IL2.
Okay, sir. Okay.
Yeah, by controlling, that's what now, controllability. Now here, what is the controllability? You have to control IL1 and IL2. IL3 will be automatically controlled because it's algebraically depend on IL1 and IL2. Clear?
Yeah, yes.
Yeah. Okay.
Sir, you were telling that we are having software where we can we can draw the bond graph over there, and we can get the state space equations directly. So, which
Yes,
is that?
that's the software name is 20sim.
It is open, sir, or that
No,
is,
no,
like
this is not open software. No, this is the commercial software, but not so costly also. It's okay. It's actually a mechatronic modeling system. So mechatronics is a multi-domain system. So bond graph is heavily used in modeling of mechatronic systems because it's a multi-domain system, right? So 20sim is a general software where the bond graph module is available. You can model the bond graph. So just quickly I browse to this. Okay. What will be the difference between signal flow graphs and bond graph? Now here you will realize the power of bond graph and model equations. So SFGs and bond graph, how they differ from each other. You must have gone through SFGs, right? Signal flow graphs. You must be aware
yes.
of it.
Yes,
Right?
sir, yes.
So what is the difference between block diagram, signal flow graph and bond graph? That is very important comparison. That's why I want to, those who are aware of signal flow graphs and block diagrams, they will immediately make out the difference. What is the difference? Now here you see the series RLC circuit. So where the bond graph is one junction and VS, R, L and C. Now as we have discussed, there can be three causal assignment possible. One is fixed, VS is fixed, right? But RLC can be interchanged. So now you can see, this is the first causality assignment, right? Where because you know one junction rule, only one causal bar can be away, other causal bars should be near. So block diagram, corresponding block diagram for this is the corresponding block diagram. You can write the equation and confirm it. And this is the corresponding signal flow graph. Now, if I assign a different causality, this with second causality, note bond graph is same, causal assignment is different. Okay, causal assignment is for what? To obtain equations. Are you getting my point? Bond graph is same. Bond graph is what? This is the bond graph. But now you have to assign causality to obtain equations. So this is then this is second type causality. So now you can see the block diagram and signal flow graph. Is it different from the earlier one? Yes or no? Now This is the third causal assignment. Now you can see corresponding block diagram and corresponding signal flow. Is it different? Yes or no? Okay, I'll give you an example. For this causal assignment, the previous one, the first one, what are the equations? Both are integral equations because we have assigned integral causality to both. So in block diagram it reflects. Yes or no?
Yes, sir.
Yes, sir.
So corresponding signal flow graph. Now here the second equation, the second causality assignment. So the L has a derivative causality while C has an integral causality. So 1 by R, so you can see that here L is nothing but dIf by dt and 1 by C I dt. So still integral causality of C is maintained. So the equation, the corresponding block diagram is different. However, bond graph is same. Signal flow graph is also different. Similarly, all the causalities are derivative causalities for L and C as well. So you can see both equations are derivative equations and the corresponding signal flow graph is different. So with the differential. So what is the takeaway message? What is the takeaway message here?
So,
Ah,
sir, the direction of these arrows can be. Sir, how can we define the direction of these arrows?
direction of the arrow.
Yeah.
Generally
then-
for this, the direction of the arrow is fixed for R, L and C. Right?
Can
We are assuming that energy is going in there.
Can we place the C arrow in upward direction?
No, it means that it is supplying the energy. Indirectly, it should be there. If it is, let's say, minus, if the total power is minus, that means C is supplying. This is for writing the equation.
So, but that do happens like when the circuit is behaving differently in on state. Like I'm taking example of DC-DC converter, and it is behaving differently in off state. So,
Yes.
at that time we can reverse the arrow.
Yes, but you can see the generally we have seen the elements earlier, right? The direction is fixed there. Assuming that the power is going inside the element. That's why I taken the simplest example.
Yeah, but it will dissipate the energy whenever it will get root or time.
Yes, what?
So, but it will dissipate its energy. Like always, we can't consider that it will.
No.
It will be
Energy,
consuming energy.
see, energy is stored in L and C and dissipated in R. So that's why it is showing away from the junction. The direction is away from the junction. While Vs is supplying effort or Vs is supplying power to the all other elements. So that's why it is near to the junction. So what is the equation then? If I say Vs, Is, let's say these are linear elements. So Is into R is the effort. Is and EL, again EC and Is. So what is EL? L ds by dt. What is EC? Sorry, what is Is in this EC? C dEc by dt. What is EC? Vs minus ISR minus EL. Right? What is EL? Nothing but EC Vs minus ISR minus L dis by dt. Right? So you can see in the corresponding block diagram the same equation. What is Vc? Vs minus LdI by dt minus Ri. Yes or no?
Yes, sir.
Right? So what is the takeaway here? The bond graph is same, while the block diagram signal flow graph changes as per the equations. That's the message. So if I show one signal flow graph to you, that depends on the equations, but it will not give you an idea what is the circuit configuration or what is the system configuration. Okay. There is one more advantage. Let's say you have now example of RC circuit, find V0 by Vs, right? So block diagram will be what? V0 by Vs is nothing but V0 is if you completely write it, so this is a block, this is a bond graph, and this is a block diagram, correct? Now if you add one more stage, is it simply a multiplication for block diagram? While you can see the bond graph, you simply add one more stage. So it takes care of the addition in the system automatically. Are you getting my point or not? Nobody is speaking?
Yes, sir.
What is what I want to show here? You cannot cascade block diagrams, but you can cascade bond graph. It doesn't affect the original system. While you cannot cascade simply the block diagram, you have to rewrite the equation again to obtain the overall transfer function. Yes or no?
Yes, sir. You're right.
So that's the advantage of bond graph.
Yes, sir.
So now this is a summary. Foundation is energy behavior, multi-domain system can be modeled, causality features gives cause-effect relation between different components, state equation can be obtained by visual inspection. Just by visual inspection you can obtain the state equations. Now we'll come to our technique. How much time we have now? Organizers?
And this is a but you can take
Huh?
10 minutes.
Yes?
10 minutes, sir.
5-10 minutes?
The time is up, but you can take your time.
Okay. Okay. I'll quickly now, sorry for the, but I hope that you must have felt interested in this.
Yes, sir. It was interesting.
If I would have quickly covered, then further part you will not understand. That's why I have taken. Now this part you will understand easily. So why bond graph and power electronics? So power electronics is a multi-domain system. Then it is ideal technique. mathematical model can be easily obtained by inspection. One-to-one correspondence is present between electric circuit and bond graph. So that's the main idea here. How we say one-to-one correspondence? From here itself you can notice it. RC, 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 right? So one-to-one correspondence. So that's why we want to use it for power electronics. But there are some fundamental issues there. So I have taken the case of switch mode power conversion, PWM DC-DC conversion. So using the bond graph, we need to model switch mode power conversion and better insight and analysis procedure for magnetic domain components. So first problem is modeling up switching, right? These are the problems. So, and because bond graph doesn't have a switching model, then because and power electronics switching is basic. Absence of standardized procedures for in bond graph for getting large signal, steady state, small signal, and magnetic electric domain model. So first, how will you model switching systems? The bond graph actually originally modeled to model continuous system. Okay, in the sense there is no switching there included. But there are several methods proposed, but accepted methodology is not there. So what we have done is we have proposed the two junctions called switch power junctions. So these elements are generalization of existing junction elements. Okay. So we know that already seen two junction elements 0 and 1, and net power flow through junction is always 0 because that's why junction element is power conserving element. So if you see the general thing here, the sum of efforts of associated bond is 0. Flow at all junction bonds is same. Equation of the junction is these are the equation of the junction. At 0 junction same we have. Effort of all bonds is same, and equation of the junction is given below. And sum of all flows at associated bonds is 0. So with causality assigned, only one bond decides the flow. Efforts at the bond flow decider is sum of the efforts at all other bonds. Junction flow is F5 here, and equation of junctions are given below. You can make out here now. Now you can make out easily here. E5 is E1 plus E2 plus E3 plus E4 after assigning causality, while all other flow is same. Similarly, at 0, only one bond decides the effort. Flow at effort decider bond is sum of flow of other bonds. So E5 and equation of junction is like this. Now, if I assign two effort deciders, which is bonds at 0 junction, this is unacceptable, right? There cannot be two effort at the 0 junction. In the conventional bond graph, do you agree? Yeah.
Yes, sir.
So now, if I make some arrangement that they are mutually exclusively applicable, like E4 and E3 are mutually exclusive. That means when E4 is present, E3 is not there. When E3 is present, E4 is not there. Then it is possible, right? So we have symbolized that 0s junction. Is it clear what I am saying? Okay. So that's what we are doing here to model the switching. So now you can see that at junction effort is U1 E3 plus U2 E4, and junction flow is F3 is U1 F1 plus F2, and F4 is U2 F2 plus F2. Now U is coming there as a Boolean or as a switching purpose. So U1 and U2 are mutually exclusive to each other. Similarly, you can apply the dual of it at a 1s junction. So this is the junction flow will be U1 F3 plus U2 F4, and similarly E3 will be E1 plus E2 U1 and E4 will be U2, E1 plus E2. And you can generalize this for n number of bonds, switching bonds. So this is our proposal. Now, how we can model this to model power electronic system? So decides the role of activation bond is decide which bond to be activated in the switch power junction, acts as an interface between energy and information domain. So now switch power junctions. Why the name switch power junctions? So now the 1s junction, the net power flowing through junction is E1 plus E2 is F3. When U2 is active, E1 plus E2 is into F4. So net power flow through the junction is switching. That's why it is called as switched power junction. Is it clear? Okay. So now what are the applications? Take voltage in series with resistor. So U1 and U2. So you can model this as activation bond. U2 is SF0, that is current is 0, and U1. So this is one example. This is the simplest example we can have. So when U1 is active, the junction flow is Vg by R. When U2 is active, junction flow is 0. Similarly, when this U1 is E2 is U1 Vg and E3 is U2 Vg. Power electronics, we have SPDT switch, which can be realized using two SPST switch. I hope this is known to you, SPDT and SPST, right? Okay. So now especially in switch mode power conversion, we use SPDT switch representation. So that's why you can represent this as a like this. The bond graph of SPDT switch is a combination of two 1s junction and 1s junction, 1 0s junction. Now you can see the boost converter. This is the SPDT switch we have modeled. Now we model this as this is the bond graph of the boost converter. And we can immediately obtain the equation. Note here, there are Boolean variables present in the system. State equations. Now it is clear to you how to obtain state equations. Now only thing is now there are Boolean variables added in the system. Similarly, there is a Chuk converter. We can easily model, and this is the bond graph of the Chuk converter. I'll skip this point. In other domains also we can model the switching. This is kind of a boost converter. This is a pump, hydraulic ram pump. When this wall is closed, check wall is open. When this wall is open, check wall is closed. So what is the purpose of this is to send this pump sends the water at the higher heights than the water source. Is it clear? Water source is at lower side, and where we have to send water is at the higher point than the water source. So this kind of a arrangement we make. So here, when the west gate valve is open, check valve is closed. When the west valve is closed, check valve is open. Right. So this is similar to what? So this is one junction. This is another junction. So this can be modeled as switch power junction. And this is similar to boost converter. Right. Because boost converter higher potential we get than the input side, that is kind of a sending water at a higher level. So I'll quickly do this. So with this, we have done some work on the how to obtain the large signal steady state and small signal model. So there are multiple way of modeling power electronic switch mode power converters, that is analytical, circuit oriented and graphical. So SIM SPDT switch, we have already seen this, and we can obtain large signals, average large signal, steady state and small signal easily with the graphical procedure we have proposed. I will not go through it right now. These are the procedures I have proposed. But you can easily obtain with this procedure, you can easily obtain on the graph itself the small signal model of the any DC-DC DC converter, even in DCM mode. Okay, so this is our example boost converter. This is a large signal model. This is large signal equation state space. Then you can average it on the bond itself. The average model. This is a steady state model. Or no, this is a small signal AC model. Okay, so you can obtain the small signal AC model as well. So I'll skip the DCM case. This is interesting part. Modeling of magnetic component. This is really a multi-domain. Now here, I'll take 5 minutes. How you model magnetic circuit in how you have learned the modeling of magnetic? Which model you have used? With inductor, any magnetic circuit, you have used flux and MMF model. Flux as a current, MMF as a effort, correct? Voltage. But here, the product of flux and MMF is not power, but it is energy. But while in bond graph, the product of effort and flow should be power. Power, right? So the modeling approaches, these are the modeling approaches: resistance and reluctance, and gyrator and permeance. So gyrator permeance approach is used since it is consistent with the bond graph philosophy, which is what effort into flow must be power. So in gyrator, the effort is MMF, flow is flux rate, not the flux. Permeance is treated as analogous to capacitance, and gyrator acts as an interface between electric and magnetic domain. So this is the thing here. Voltage V, magnetomotive forces MMF. So this is the analogy. Current is flux rate, capacitance is permeance, charge is flux, permittivity is permeability, power is MMF into d phi by dt, energy is E into MMF integral of d phi. So that's the comparison here. So let's say modeling of inductor, right? So boost converter with C core inductor. So you can see here there is a gyrator, and you can model the inside of the magnetic component. So this, if I take this as a linear capacitance, as well as I can take it as a non-linear capacitance, which can include the hysteresis effect. So this is the model of inductor with causality. Similarly, you can model the leakage and core loss effects as well. With the core loss, you can model it as a resistor. You can see here RC, and the leakage you can model it as a sigma G here, lambda G here. So this leakage effect, you can also model the transformer with the gyrator permeance approach. Similarly, you can model the forward converter with this, even the center tap converters with this approach. So modeling of transformer and switch power junctions are extensively used. You can see here, because of there is a complex phenomena of switching as well as the magnetic components. You can also model the integrated magnetic components with the bond graph, and you will get a good insight when you model these components. So in summary, modeling of switching phenomena is bond graph is possible, and we have proposed also procedure of obtaining large signals, average large signal, steady state small signal, means we have very briefly discussed, and modeling of magnetic SMPCs in both in magnetic and electric domain we have discussed. So two switching junction elements we have seen. These are representation of generalization of conventional 0 and 1. All the switching modes on the same bond graph represents only physical modes. State vector doesn't vary with change in the switching mode. Numerical stiffness in minimized and application to any energy domain. So these are the things we have seen, magnetic as well as the switch mode power conversion elements. Thank you.
Thank you, sir.
Sorry,
Thank
the
you,
last important part I have rushed through, but I think time permits, then we could have done. But I also have some engagement. Yeah.
Thank you so much, sir. Any questions from participant side, please?
Size of the transformer, no. Size of the transformer is different. Okay, you can model inside of the transformer. That is what the model the loss, model the permeance to study what will be the overall performance. The size of the transformer is a totally different issue.
Can you name some simulation softwares for this bond graph?
Or
Where we can simulate this bond graph. Software
20 sim.
20 sim. Okay.
Yeah.
Okay, sir.
I hope you have got something from this something from this lecture.
Sir,
Yes,
the
sir.
The
question
introduction
is,
to
sir,
yes.
sir, the question is being asked that how to simulate these bond graphs in which software?
20 sim. That's what I answered. 20 sim.
Sir, where I'll get the literature of this, because the last part has been rushed because of the time. Time was less, so like that was the major part, like how to average on state and off state.
There is one of my
And-
paper is there in IET IEE electric power applications. Name switch modeling of switch mode power converters. See, a simulation platform I had when I have developed in Simulink, but right now it is we have to find out. Okay, this simulation platform I have developed while we can also use the 20 sim as well, because 20 sim was not available to us. So that's why we have used the basic equations and use this in a Simulink.
So what you told about the modeling of the couple inductor and transformer, it was like the basic inductor that you have modeled in bond graph. The same you have modeled. What is the structure of bond graph that we are getting for the transformer and for the couple inductor, including all the parasitics or
Yes.
lossy elements.
Yes, we can model all the parasitics as well. How deep you want to go, you can go. See, modeling is basically what you want to see. If you want to go more deeper, you want to see the performance, understand what will be the core loss, then your model has to be more detailed. But if you want to see basic effect of inductance, you are not interested in loss in the inductor, then you will, but you are interested in, let's say, hysteresis effect or non-linear effect, then you can model up to that point only. That capacitor you can model as a non-linear capacitor. You want to include saturation, you can include saturation. So up to which extent you want to go in the model, you can always, this is all flexible in the bond graph.
The same you can reflect in the equations.
Yes, it will reflect in the equation. In this case, I have taken all linear. Okay, but you can go with non-linear as well.
So we are very much thankful to Professor Amod sir for delivering a wonderful talk and being with us. He enlightened us with this. Very few people are working with this bond graphs actually. So I especially requested sir that other parts like state space averaging and other techniques anyone can cover, but sir has a specialty in this bond graph domain or topic. So he has nicely gave us the fundamentals things that how to start from basics for designing the modeling of any piloting systems, or maybe it's a mechatronic system. So we are very much thankful, sir, that you kindly has accepted our invitation and delivered this talk, which gave a new insight to all of us. And definitely our participants and other students, they will be using this in their researches and will be helpful to them. Thank you so much, sir.
Yeah, thank you for
so
the
much.
invitation. After a long time, I have gone through this topic. After a long time, I have given a lecture on this topic. So thank you for revising again for me. It's a good revision for me. And thank you for the patiently listening my topic, my talk. Yeah. I hope you can always contact me. I am from IIT Indore. You can check from my webpage, my contact, and you can always contact. Thank you. So can I log out now?
Yes, sir.
Okay. Yeah. Yeah. Thank you.
Morning session of day 4. Now we will have another session at 2 o'clock. So that session will be delivered by Professor Santanu Mishra from IIT Delhi. He was professor earlier at IIT Kanpur. So I'll meet at 2 o'clock. So then, till then, thank you. Bye.